So this is the third session for today's talk. So the first speaker is Soumyajyoti Biswas from SRM University, Amravati.
Good afternoon, and let me first thank the organizers for this wonderful event and giving me the opportunity to present our work here. So I'll be talking about critical scaling through Gini index. So it's the latter part that requires more expansion than the former. But regardless, let's start from a rather rudimentary point for this audience. Let's consider some response function, any response function, and there is some driving field, and it diverges at critical point with an exponent minus n, and that's of course universal. And then these two colors just represent that there are two prefactors and their amplitude ratio that is also known to be universal. The only non-universal part in this whole picture is the critical point. That of course depends on the parameters, the models, and everything else. So the goal of this talk is to write down this in the form so that there is no non-universal parameter. So that's what we try to do through Gini index. So let's just first discuss what Gini index is. So this was introduced a little over a century ago in economics, measuring the inequality of income in society. So what it says is that if you arrange all the people in ascending order of their money and normalize, of course, then you will get a curve like this. For example, here it says that the poorest 60% of people have 10% of the wealth and so on. But then if everybody had exactly same amount of money, then it would be a 45-degree straight line. So the fact that it deviates from this 45-degree line is because there is inequality. And therefore, this area, this A divided by A plus B, that's a measure. That's one measure of inequality. And that's called Gini index, and that's been in use for quite some time. So what we want to do is to apply this or measure this inequality in the case of a response function for critical system. So of course, if you start from some point A of Fc and go up to B of Fc, the response is going to be unequal because you are changing your driving field. And you can write down the expression for the Lorentz curve, so that this curve is called the Lorentz curve. So that you can write down, and from there you can calculate the Gini index. And then given it's a simple power law form, you can evaluate these integrals. So it turns out to be like this, and it has a few parameters. That's n, of course, the exponent, a and b as the starting and the finishing point. Now, in this expression for the Gini index, let's take the limit b going to 1. So what does b going to 1 mean? Here, as you can see, b going to 1 means that you are actually calculating up to the critical point. If you take the b going to 1 limit, or in this range where n is between 0 and 1, this a dependence where you're starting from, that cancels out. You can see from this expression, well, at least believe me, then it would be n by 2 minus n. So it's only a function of n and not anything else. And then you can expand this in a Taylor series for 1 minus b, so near 1 minus b. And of course, this is the first term, and then up to the leading order, I mean, the next term, you get this. So what is this? This is 1 minus b to the power something. Now 1 minus b is what? If you look again, 1 minus b is f minus fc actually, divided by fc. So if you write g minus gf, which I have done here, you essentially get 1 minus, rather f minus fc to the power 1 minus n, which means f minus fc would be g minus gf to the power 1 over 1 minus n. But then our response function was f minus fc to the power minus n, so which means now we can write the response function as g minus gf to the power minus n bar 1 over n. And then this gf is now only a function of n, not function of anything else. You can actually go on do this for other limits, like between 1 and 2, you will have minus n over n minus 1, then gf would actually be 1, which I should have written somewhere. Yeah, gf goes to 1. And then for greater than 2 also gf will go to 1, and this would be the scaling. So in summary, you will have something like this. If you start with a response function in this form, you can write it down always in terms of g minus gf to the power something. That something, of course, changes. And this GF always remains a function of n or is a constant, which means you are always able to write it down in terms of universal quantities. You don't have to, so basically it's one scaling form for all models of any critical phenomena. And this is just numerically, I just tried to show, because we made this LCD, so how far is that valid? You could see that it gives the expected results. Now let's just do a few examples. We can start from the Ising model in the mean field limit. That of course gives you an order parameter that is Tc minus T to the power half, but then that is not diverging, so what we wanted something that should diverge. So let's take a derivative with respect to T, that will give you minus half, which means if you compare with our starting point, then n is half. So if you put n half here, you get 1/3, and it's easy to show that you will get the magnetization, that the order parameter is linear in G minus GF, what you see here. And this is actually true for any order parameter. It doesn't matter, I mean, it doesn't have to be half. Actually, that's quite easy to show. If you start with anything to the power beta and take a derivative with respect to the field, you get beta minus 1, but beta is less than 1, which means this is negative. So your n is 1 minus beta. But then T minus Tc should be 1 over 1 minus n, which means m should be beta by 1 minus n, but beta is 1 minus n, so you will always have this linear scaling, irrespective of which order parameter, I mean, whatever is your order parameter exponent. The other than the last example is that of a model for fracture. It's a fibroblast model, it's a mean field model. I will not be explaining what that is, but it's a mean field model that basically you are increasing the stress and eventually the system collapses. So there also you have the similar half and this mean field, so you'll get half again. Now if you take a derivative, so sigma here is a stress, you get something like this. And here it has a physical meaning, it's actually the avalanche. And again, the order parameter is linear, that is expected. But then the thing is, here it is important to know how far you are from the critical point. I mean, it might be in many other contexts as well, but at least in case of fracture it is, because you want to know when this catastrophic breakdown is going to happen. So for example, if you have a bunch of samples, they're very heterogeneous, so they have different failure thresholds, different distributions and so on, you will have the critical point basically anywhere. I mean, this is time, but time is, this is linearly loaded, so this is a proxy of the applied load. So the critical point could be literally anywhere, but as long as you are in the same universality class, of course, which you are, this GF is rather well defined. This is something actually we noticed before when we tried to feed a machine learning algorithm with various attributes, and G was one of them. And machine learning algorithm at that time correctly said in its feature importance that more heterogeneous is a system, Gini index is the most important thing. It's almost 100%. Yeah. So this is log scales. That is basically everything, and everything else was much less. But at that time, we didn't understand why, but now we know that this would be the reason. So in summary, this is just one sentence, is that for any response function that can be written this way, you can write it in this form, where GF and N star are at least as universal as your critical exponent. And this could be useful for predicting imminent criticality. I gave one example in fracture, but I'm sure there could be other uses. This work was done by Soumyajyoti, who is my student, and Diksha did the previous work on machine learning, and Narendra also works on fracture, and this nice looking view of our campus. And yeah, thank you very much.
Any questions? Okay, so if there is no questions, so we'll go, let's thank the speaker.